Have you ever wondered how electronics make decisions? It all comes down to logic gates and flip-flops. These are the fundamental building blocks of everything from microcontrollers to memory chips to processors. My name is Zach and I'm the Byte-sized engineer. In this video, we're going to break all of that down and simplify it using an interactive demo that I built using a couple of switches and an LED. To start out this video, I'll focus on talking about logic gates, and then a little bit later on, I'll talk about flip-flops. Oh no, that fly is back. Got it. Now, where was I? Oh, that's right. I've drawn out the symbols for 3 different logic gates here on these sticky notes. The first logic gate that I want to talk about is the AND gate, and this is the symbol for it. It's got 2 different inputs and 1 output. The second logic gate is an OR gate. It also has 2 inputs and 1 output. The third logic gate is a NOT gate. It's also known as an inverter. It's got 1 input and 1 output. Logic gates aren't just some mystical devices that appeared out of nowhere. They're actually made out of transistors. To show you what I'm talking about, I've drawn a schematic for each of these types of logic gates. First, let's take a closer look at the AND gate. Like I said, it's got 2 inputs, and on this schematic, those inputs are represented by 2 different switches. The AND gate has 1 output, and on the schematic, I went ahead and I connected that output to an LED. Next, we've got the OR gate. It also has 2 inputs, which are represented by switches on my schematic, and I've connected the output to another LED. And finally, we've got the NOT gate. This has 1 input, which is represented by the 1 switch, and the output, again, is represented by an LED. But how do these logic gates work? How do they actually make decisions? Well, let's go find out by looking at a simulation on the computer. I've got the simulation open. From left to right, we've got the AND gate, the OR gate, and the NOT gate. Let's start playing around with these switches to see how these logic gates behave. Before I move forward, if you want an extra challenge, pause the video now and draw out these circuits. You can analyze them and see how they behave. So I've got 2 different switches, which means there are 4 different states. I'm gonna close the first switch and the LED remains off. I'll open the first one and then close the second one. The LED is also off. But what happens if I close both switches? All of a sudden the LED turns on. That's kind of interesting. Okay, so let's move on to the OR gate. Again, we've got 2 switches representing the 2 inputs, and when they're both open, the LED is off. Let's close the top switch, and I can see that the LED turns on. What happens when I close the bottom switch? The LED turns on. What happens if I close both switches? The LED is also on. Okay, interesting. Let's move on to the NOT gate. This one only has 1 input, which is represented by the 1 switch. When the switch is open, I can see that the LED is on. But if I close the switch, the LED turns off. I want to write those results down in a table. So let's create a table for the AND gate. We've got 2 switches, which we're going to call switch A and switch B. Then we have our output over here. When a switch is open, there's no voltage flowing through the base of the transistor, which means it's off. Instead of referencing the voltages here, I'm just going to use the binary number 0 for off and the binary number 1 for on. The first state of A and B is open, open, or 0, 0. And when that happened, the output was off, so I'm going to put a 0. Then I closed switch B, so that would be 0, 1, and the output was also off. Next, I closed switch A and opened switch B, and the output was still 0. Then finally, I closed both switches, so the inputs were 1, 1, and the output was 1. So this table describes the behavior of the AND gate, and there's actually a name for this table. It's called a truth table because another way of saying 1 and 0 is true and false. Here are the truth tables for the other 2 logic gates. If we look at the truth table for the OR gate, we can see that if the input is 0, 0, our output is 0, but for all the other configurations, the output is 1. Now, if we look at the NOT gate, which is also known as an inverter, the output is simply the opposite of the input. So if our input is 0, the output is 1, and vice versa. Now let's do something interesting. I can create a new logic gate by attaching a NOT gate to the output of an AND gate like this. This creates a new logic gate called a NOT AND gate, or NAND gate for short. The symbol is very similar to an AND gate, except that it has a circle on the output, which indicates that it is inverted on the output. You can actually do the same thing with an OR gate, making it a NOT NOT OR gate, or NOR gate for short. If I were to write a truth table for the NAND gate, it would look exactly the same as an AND gate, except that the outputs would be inverted. So all of the zeros become ones and the ones become zeros. Similarly, the same thing with a NOR gate. The output is the same as an OR gate, except it's opposite. All of the zeros become ones and the ones become zeros. Finally, I want to introduce one last logic gate. It's called an exclusive OR gate. It works very similarly to the OR gate, except that if I want the output to be 1, I need the inputs to be exclusively different from one another. When the inputs are the same, like 0, 0 or 1, 1, the output is 0. When the inputs are different, I get a 1 on the output. And of course, we can always add an inverter to the output, creating an XNOR gate. These 7 logic gates are the fundamental building blocks of all digital design. Notice how all of the inverted outputs have a little circle on them. This is sometimes called a bubble. By combining these logic gates, you can create really complex decision-making behavior. Since this is an introductory video, I'm not going to go down the rabbit hole, but if you're interested, let me know down in the comments, and I'm happy to make another video in the future where I dive deeper into this topic. We can go over Boolean algebra and sequential and combinational logic and De Morgan's law and Carnot maps and all of that. All right, that's enough theory. I'm tired of talking about this and drawing things on sticky notes. Let's bring these concepts into the real world. I'm definitely a visual learner. I like having tactile things that I can hold in my hand. So that's why I built this digital sandbox that lets me experiment with all of the logic gates that we've talked about so far. Basically, it's just a microcontroller inside here on a breadboard, and it's got 2 buttons and an LED. So let's give this a shot. And to make things a little bit interesting, let's see if cameraman Pat was paying attention. We're gonna quiz him on the logic gates. Are you ready, Pat?
Let's give it a shot.
Okay, all right, the first one is an AND gate. I'm gonna cover up the truth table, and you can tell me what's gonna happen if I press button B.
It's gonna light up.
It's gonna light up?
Yeah.
Oh, no. What about button A?
No.
Okay, good. All right, do you want the truth table?
Of course I want a cheat sheet.
Okay, all right, here's your reference. So if I want to turn on the LED, what do I need to do?
You need to hit both buttons.
Okay, good job.
Hooray.
Perfect. All right, next one, let's go with the OR gate. I'm gonna cover up the truth table. All right, what happens if I press button A? Does it light up or no?
It will light up.
Light up? What if I press both of these?
No.
It does.
It does.
Yes, because it does light up because if you look at the truth table here, A and B are 1 and the output is 1. All right, I'm gonna give you something a little bit more challenging. All right, let's go with the NAND gate. What happens if I press button A? Does it turn off?
No.
Okay, you are right. What about button B?
No.
All right, now I'm gonna press them both. What happens?
It's gonna turn off.
All right, looks like you were paying attention. All right, we're gonna go for broke and we're gonna go with the hardest one that I have. The exclusive NOR gate. Okay, so the LED is on. What do I need to do to turn off the LED?
Either button.
Either one. So I can press A and it'll turn off?
Maybe.
Maybe. There's no maybe in digital logic. It's definitely something or the other thing. Yes. Oh, good job. That's pretty impressive, Pat, especially for not having a background in electronics. This tool is an awesome hands-on way to learn about logic gates. I've got a whole bunch of different card inserts here that I can use like flashcards and challenge myself or just give myself a little bit of a refresher. Individual logic gates are cool, but the real power comes when you combine them together. We started with transistors and we turned those transistors into logic gates. Let's turn these logic gates into flip-flops. Flip-flops are what allow us to store data and give our circuits memory. So logic gates on their own can make decisions. Flip-flops actually remember the state of things. So let me show you the most simple flip-flop I can make, which is an SR flip-flop. What happens when we combine 2 logic gates into a circuit like this? I've got 2 NOR gates and they are cross-coupled, which means the output of one is fed into the input of the other. And so when we combine logic gates like this, we get something interesting. We still have 2 inputs. We have a set and a reset and 1 output, which I have tied to an LED. When both of the inputs are inactive, they're both 0, our output just stays the same. Whatever it was before, it will remain the same. However, when we activate the set input, the output gets latched high. It doesn't matter what happens to the set input, the output will remain latched high. Likewise, we can activate the reset input and the output goes low. No matter what happens to the reset input, our output remains latched low. The fourth state is actually an invalid state. It's when both the set and reset inputs are activated at the same time. It causes a race condition and the logic breaks down. So we need to avoid that input state. I've gone ahead and I've written out that truth table here. We've got 0, 0, no change, 0, 1, the output is 0, 1, 0, the output is 1, and 1, 1 is an invalid state. So let's see what that looks like on our digital logic sandbox. So we've got both inputs are 0 and our output remains the same. So if I press the set, we can see that the output is latched high. It doesn't matter what the inputs are, it remembers that state and it remains the same. So I can keep pressing set and nothing happens. Or I can press reset and the output goes low. It's latched in that state. No matter how many times I press that, it stays that way. Now let's do the fun part, and we're gonna input the invalid state here. And it lets us know by blinking and making a tone. This is great, but having an invalid state like this is not acceptable. So let's fix that problem by creating a D flip-flop. This is a D flip-flop and it improves on the SR flip-flop. So here's our truth table for the D flip-flop. We have our input is D and it can only be a 0 or a 1. And then we have a clock input. And our output only changes on the rising edge of the clock. That means when it changes from a logic low to a logic high, we get that rising edge and the output will change. And our output will match the input on the rising edge. Let's look at the logic diagram. We still have our two NOR gates that are cross-coupled, providing that feedback, but we've added two AND gates and an inverter. Unlike the SR flip-flop, which has an invalid state, the D flip-flop only has valid states because we're only reading our inputs on the rising edge of our clock. But looking at this on a piece of paper is boring. Let's take a look on the digital logic sandbox. I insert that card and we have a D input and our clock input. So right now it's doing nothing. And even if I press the D input, nothing happens because there's no rising edge on the clock. So I'm gonna hold down D and give ourselves a rising edge of the clock. And we can see that the output gets latched. I can let go of D and now that output is gonna stay the same no matter what. Now I can reset it by leaving D unpressed and I give it another rising edge and that resets the flip-flop. Basically, a simple way to think about this is anytime I press a rising edge on the clock, the input gets mirrored to the output. I can set this flip-flop or I can reset it. Let's take this one step further. We're gonna build a JK flip-flop. I'm not kidding, no joking around here. It's called a JK flip-flop. The JK flip-flop is a great example of how these components can be used to build bigger and more complex things. I'm using an SR flip-flop as the basis, but I've got two NAND gates that are tied in and cross-coupled like they were before. We also still have a clock input, and we're only looking for changes on the rising edge, but now instead of just one input, we've got two inputs called J and K. And if you can tell me what those stand for, I would really appreciate it. The truth table for this one is very similar to the D flip-flop, except now when we have both inputs activated, we can toggle the output. So let's see what that looks like on the digital logic sandbox. The digital logic sandbox only has two buttons and we need a third thing to represent the clock signal. So I've generated a tone that turns on and off to simulate that rising edge of the clock. So when I put this tile on, you'll hear a tone beep every 1 second. So 0, 0, our output is unchanged. 0, 1, we've got a 0 on the output. 1, 0, latches our output high, and then 1, 1 will toggle it on and off. Let's take this off so that it's not beeping and summarize what we've learned so far. We can use transistors to build logic gates. Logic gates are what allow electronics to make decisions. Then we can combine logic gates into flip-flops, which store memory. On a basic scale, this is how computers make decisions and remember things. So how would you practically use these? Well, the easiest way is to get an integrated circuit chip like these that DigiKey sells that has logic gates and flip-flops built into it. That's exactly what I did a long time ago when I was in engineering school. I wanted to build a hands-on practical way to learn about logic gates and flip-flops, and so I've dug into the Byte Size Engineering archives and I found the original circuit boards that I built while I was in school. These are some of the very first PCBs that I've designed and they kind of have a soft spot in my heart. This one here has a whole bunch of logic gates on it. On this side, I've got 10 different OR gates, and on this side, I've got AND gates, and then I've got NOT gates in the middle. And if you look on the back here, these are the chips that actually have those logic gates baked inside them. This board allowed me to build these circuits in real life. I had some jumper wires and I could connect everything together and see how things worked. These chips come in both surface mount and through hole, so you can use them to build a circuit board like I did, or you can use them on a breadboard as you're learning. This was a perfect way for me to learn how all of this works in a real hands-on way. I've barely scratched the surface of what you can build using logic gates and flip-flops. From here, you could build simple adders or even simple calculators. Really, these are all the building blocks of modern microcontrollers and microprocessors. There is still so much to learn about this topic, so if you want me to cover something specifically, let me know down in the comments. My name is Zach, and I'm the Byte Size Engineer. Thank you for watching.